Thanks for the introduction. And just as a disclaimer, this talk is going to be just a general introduction of different types of attacks and certifications, and not really a deep dive into just one method or one paper. Okay, so firstly, I'll introduce the problem and why we actually need this robustness. Then we'll look into the construction of adversarial examples. We'll try to see how we can improve the robustness, more specifically using the technique called adversarial training. And then in the end, we'll see if we can get any certifiable robustness, so any guarantees on robustness. We'll look into exact verification, which is the complete guarantee. Then we'll go into techniques such as convex relaxations, Lipschitz continuity, and randomized smoothing, which don't really give a certain guarantee, but they still work pretty good in practice. Often we have these different machine learning models and algorithms which are optimized with respect to just simple metrics such as accuracy and misclassification rate. But as machine learning is becoming more widespread and is being applied in fields such as autonomous driving, so these high-risk fields, and another example is the applications in health and some algorithmic decision-making which involve humans, such as the hiring process. So in these cases, we do actually care about not just the correctness, but also the robustness of the models, because when these algorithms get deployed into the real world, we usually don't know how they will behave when they're given an actual real data in the real world. Or also, we need to be sure that these are reliable, not just because of the real data that we will get, but also for the attacks, for the fake data that some people generate. And so we want to be sure that our algorithms perform good even when the data is corrupted. What are the adversarial examples? Let's look at this image of a pig, which we, for example, give to our neural network model. And well, we hope and we actually do get the prediction of pig, which is the correct one. But the problem is that when we add just a small noise image to this data, even though for our human eye, the final image, which is this original one plus an adversarial perturbation, even though this final image for us humans is almost the same as the original one, in fact, many very good performing models actually detect that this is an airliner and not a pig. And so this shows that, and there are many more examples like this. It's not just this one. So this shows that small and these imperceptible changes that we don't see as humans, they are specifically crafted to lead to false predictions in these machine learning models. And we do actually care that we don't just give false predictions when the image is clearly the same one. So a few important questions that we might want to ask is, first of all, why should we really care about these adversarial examples? And then what does this small perturbation mean? How small can it be? And then how are these adversarial examples actually created, because they're not just random? And also, one important thing is how to protect against those adversarial examples. So yeah, the first one, why should we care about these examples? There are, first of all, many real-world risks connected with these adversarial examples. First one is the obvious security threat in, for example, self-driving cars. So yeah, we'll see in the next slides that for example, road signs may be misclassified, even though for the human eye it's perfectly clear that it's this specific road sign, and it's a high risk for self-driving cars. And another example in the real world, again, we'll see in the next slide, is the when, for example, we have glasses in the picture. The human is wearing glasses, and suddenly he or she is misclassified due to only wearing glasses. So they're classified as a different person. Besides these real world risks, we do have these conceptual gaps as well. So in neural network research, we do sort of rely on this hypothesis that the neural networks are supposed to learn meaningful representations that do capture this semantic understanding of the domain. And so when we have these adversarial examples, even though the semantic meaning does not change, we see that neural networks sometimes perform poorly in their field. Also, we do have nature as an adversary as well. So even if there's no one creating this fake data that wants to fool our model, we still should be robust to the worst case normal, just natural noise. So yeah, as I mentioned, these are just two examples in the real life, so not specifically curated to fool the networks. But on the left, we see how adversarial glasses, so I think these are 3D or 2D printed glasses, and they're used to fool the facial recognition system. So on the first line, you can see the input, and well, on the second line, you see images of those people who were classified as. So, for example, the first male person was classified as the actress on the bottom. And and on the right, we can see the stop sign, which only has a couple of stickers in it, and it is misclassified as a speed limit. Okay, so to give more formal definition of these adversarial examples, say we have a classification task, and we have a data set consisting of xi and yi points from our data distribution, and xi's are d-dimensional vectors and yi's are just the labels. And we also have the F classifier, which takes the inputs and gives the output y's. And we also want to specify a perturbation set pi of x, which is the set of perturbation when that we apply on x that are not supposed to change the semantics. So they do sort of change the data, but not really the semantic. And so since the semantic should be the same, we should also get the same class as before. And we say that a point x tilde in this perturbation set is an adversarial example for the function f at this point xy, if we do have x correctly classified, but the perturbed image or perturbed data x tilde is not correctly classified. Okay, on small perturbations, how small is this small, and how do we define that? So again, these perturbations should not really change the semantic content of this sample, and these are often translated to LP constraints with some small epsilon. So just as a reminder, the LP norm would be this, well, P can be any natural number and infinity, but usually in these scenarios we take even either L1, L2, or L infinity, and then the perturbation set P would be given by this this formula here. And then also, while these LP sets are the sets with LP norms are mathematically convenient, these actually do not obviously capture all of the semantically meaningless perturbations. So, for example, one counterexample would be that a small rotation of the image should not change the meaning of a picture, but often it corresponds to large changes in these LP norms. So what types of attack variants are there? First of all, we have this first grouping of evasion attacks and poisoning attacks. We'll mostly focus on evasion attacks in this talk. So this is when we have a fixed and already trained classifier F, and the attacker wants to find perturbations, so wants to fool the network at test time. And in contrast, poisoning attacks is when the adversary wants to modify the training set and then obviously train on this training set so that the classifier trained on this changed data set has properties that the attacker desires. So it's basically fooled. And another grouping of attack variants is these targeted attacks and untargeted attacks, where in case of the targeted ones, we, not us, but the attacker wants to have a specific, so that the specific sample classified as a specific class. So they want, for example, the stop sign to be classified as a speed limit sign. And untargeted attacks is when the attacker just wants to misclassify this given sample and doesn't really care about what class is going to be classified as. When we want to construct these adversarial examples, this problem can be phrased as the following optimization problem. We want to maximize the loss instead of the usual, the training of neural networks where we want to minimize the loss. Here we want to maximize to see the worst possible perturbation. So we call that the L01 is the 0-1 loss, which is 0 when the classification is correct, the prediction is correct, and it's 1 if it's incorrect. But the problem with the L01 loss is that we either have 0 or undefined gradient. So in many cases, we just use the cross entropy loss as the surrogate to it. And so we have this this new objective function underneath. And this is similar to training a model, but instead of updating the parameters so that the model gets better and better, we do actually update the data and so to find the worst possible perturbation. But since this F is not convex, as it is it's not in usual neural networks, we cannot be sure to find the global optimum. And as you can see, this is a constraint optimization problem. Instead of the stochastic gradient descent and the other algorithms similar to that, we will use algorithms specifically designed for constraint optimization, for example, a projected gradient descent and fast gradient sign method. How can we improve robustness of our model? So even though our most machine learning models are vulnerable to adversarial examples, especially for that, we want to be able to defend against adversarial examples. We want to prevent them beforehand, and just in general to improve the robustness of our model. So just a general idea of what does not seem to work for these problems. First one, the post hoc prevention of attacks. For example, gradient obfuscation, such as randomizing or shattering the gradients of the model. So these are good defenses, but they all have been broken by stronger attacks. And the other one, the detection of adversarial examples, for example, with these out of distribution shift methods. So we want to distinguish between these two distributions, right? The real images, the natural images, and then the adversarial ones. So sort of to perform this outlier or anomaly detection. And while, again, some of these methods work against this simplest vanilla projected gradient descent attacks, these targeted attacks are actually very successful against these types of defenses. And also one note is that just generally fixing a bad performing model also does not seem to be the solution to this robustness. Okay, so I want to introduce the robust training, and then we'll go into more details of one type of it, which is called adversarial training. So robust training is this group of training procedures that want to make the model robust to these adversarial perturbations. And this common theme, common way of doing so is optimizing the worst case loss, also called the robust loss. So we'll change the normal loss that we have in all neural networks into a more robust one. Yeah, this is the loss achieved under the worst case perturbations of input. And adversarial training is one of the robust training methods. Is an easy to implement procedure that uses proxy for this worst case perturbation, so not actually the worst case one. And in the end of the talk, we'll also cover robustness certification techniques, some of which can also be used for robust training. Okay, let us have this L y hat y, which is the loss between the predicted and ground truth outputs. And for this example, we pick it to be the cross entropy loss. And so the old loss, the non-robust loss that we would have before, is this first one, which is the expected value of the, so sort of the average of all of the losses evaluated on all of the points. And the robust version of this problem would be the same average, but taken in between those the supremum of the loss under the worst, under all of the same, all of the set of perturbations. So in case the supremum will give us the worst perturbation evaluated in this loss. And for this f, depending on theta being this neural network with weights theta, we can see that the gradient of this loss with respect to the these weights theta is this one given underneath. But the problem here is that we can't really use the usual gradient descent method, since we don't know how to compute the gradient of the supremum. And to solve this issue, we introduced this Danskin's theorem, which says that if we have if the set of the worst case perturbations has only a single element, x tilde star, then the supremum will be differentiable at the point theta, and we'll have it evaluated on this one, again, this one single worst case perturbation. But again, since we don't really know how to find this worst case perturb image, example, it's intractable. And well, if we could find it, then we would have already solved the exact verification problem. And the idea is to sort of create this this proxy, which will help us to use any other optimization method. And as proxy, we will take any adversarial example, so not necessarily the worst one. In summary, the adversarial training algorithm would look like this. We would firstly sample any point, well, pair of points from our data distribution. Then using this adversarial attack procedure, we will find any any adversarial example, not necessarily the worst one, just one where we get a wrong classification. And then we'll update the weights of our network. We'll do a training as usual with the, say stochastic gradient descent. But instead of X, we'll use this X tilde, which is our perturbed data point. And so just as a note, in this step 2, since we don't really use the worst case, so the most accurate X tilde, we do have this sort of trade-off between strength of the attack and the computational cost. So in this case, obviously, we prefer that we do it fast enough. Okay, so in summary, we have a couple of advantages in adversarial training, such as it empirically was shown to increase the robustness of the models, and it's also relatively easy to implement. But the disadvantages are that if we want to use a powerful attack, then it's going to be super slow compared to standard training. And then also the resulting models typically have lower accuracy on clean data, even though they perform better on these perturbed images. On the normal images, just the average accuracy sort of goes down. And then one more thing is that we don't really have any theoretical guarantees of this model's robustness. We just have that. We just know that empirically they do improve the robustness. Okay, so moving on to certifiable robustness. Why do we need it and what it is? Even though the adversarial training improves the robustness, as we just saw, we actually want to make sure that the user of the user of this network can actually rely on the results. So be sure that these are this model is adversarial free, sort of. So because why am I saying this? Because when in adversarial training, even though it generally improves the robustness, there could still exist some examples, some cases where the model is not performing very robustly, so it's giving wrong classifications. As I already mentioned, detection of these adversarial examples does not seem to work, and a better approach to this would be robustness certification, which the main idea of which is to try to prove that the value, the classifier's prediction does not change within a radius for a specific sample. And if we do actually prove this, and if it's successful, then we know that there's no adversarial examples within its radius, this radius of around our given input sample. And if the proof is not successful, if we cannot prove that it's adversarial free, then we know that the prediction could change to another class. And so there might be some samples that are adversarial. So the goal is to develop an algorithm that specifically answers to this question: is the classifier F around the sample X adversarial free? Yeah, okay. And this question is in the context of epsilon balls around this given sample X, and we get the answer yes if and only if there are no adversarial examples in this epsilon ball, and we get the no as an answer if and only if there is an adversarial example. So these types of verification methods are typically designed for ReLU networks, and since they are very prevalent in deep learning, and they're also very well suited for these combinatorial exact verification methods. But there are some methods that do work for other types of activation functions. Okay, so we just as a recap of neural networks, right? We view neural networks as sequence of functions. So sequence of nested functions, and each layer that we have is defined with this f, where this sigma is the activation function. Here we'll take ReLU, and then inside the argument of it will be just the linear function of x, where w and b are the weights and the biases of this layer. And so the overall network will be this one, this big F. And in the end, we get the logits. We don't really take the softmax here since, well, we could take the softmax. It's just that since the order of softmax outputs is the same as pre-softmax outputs, and we only care about the sort of the winning class and the next one, and yeah, since the order is the same, we don't really need to put it into softmax. This exact certification method, when we are able to achieve it, it's a very powerful method, since we know exactly when there could be an adversarial example around a point, and well, can also actually use this knowledge to get a bad perturbation and then use it in adversarial training. And but the problem is that exact certification of neural networks with ReLU activation has been proved to be NP complete in the case of L infinity bounded perturbations. But we'll still go in a little bit into that since this modern algorithms that solve these NP complete problems are still performing pretty good in case of medium-sized neural networks. So here we want to sort of describe this exact certification problem as a mixed integer linear program, and then this NP solvers will solve the problem. But as a formulation, we suppose our classifier predicts class C star for X, the best class, and we call MT this new notation, this difference between the output of the neural network for the best class, the winning class, and another class T. So this will be called the classification margin of classes C star and T. So mathematically, we do want to sort of minimize this worst case margin to be able to find a perturbed, an adversarial example. And we also have this this constraint that we want to have an epsilon on the LP constraint between the differences of the difference of our input and the perturbed sample. And so if we are able to solve this this problem, and then we get the final M star bigger than larger than 0, then this means that the classifier's prediction cannot be changed from class C star to T. So this is the case when we get a robustness around this this sample X. And this means that for all classes that are not equal to the winning class, if we have this positive margin for all classes, then we can certify robustness. And then if for some class we don't have it, then there exists an adversarial example in this perturbation set. Okay, so again, I won't go into a lot of details here, but we can write the this optimization problem like this. Again, we still have the same margin as the objective function. We have the the restriction on the epsilon ball, and also underneath we have the network, so the linear activation ReLU. And here X hat L denotes the pre-ReLU activation of layer L. And so to be able to express this as a mixed integer linear program, we do want to sort of reformulate these LP constraints to be linear, and also the non-linear really constraint should be somehow changed, because right now it won't fit under the class of mixed integer linear programs. And most of the difficulty actually comes from the ReLU. But here in this slide, we can see that we can change the objective function, and more specifically the L infinity norm part and the ReLU part to be able to solve it with mixed integer linear programming. So here we changed the L infinity norm into two linear inequalities, and then we changed really into mostly linear inequalities, but then we also have in the last line we have this AI variable, which is a binary variable, and again, we won't go into a lot of details, but basically this last part about ReLU, even though it doesn't sound familiar, it does actually equal to the exact ReLU. So there's no difference between this formulation and ReLU. It's just that we sort of need this to be able to use the MILP solvers. And also we introduce here L's and U's besides the new AIs. So these L's and U's are the lower and upper bounds that we get using interval arithmetic. So these are these bounds on output of the ReLU. So we do have the first input x, and then using this interval arithmetic, we can sort of compute around what interval this output of ReLU will be. And this helps to formulate ReLU as a MILP problem, and but also if we have this smaller bounds, so more accurate bounds, then the training will be this optimization will be much faster. So just as a summary of exact verification, it's possible for ReLU network, but still expensive for large neural networks. And we can ask the question if we can get more efficient certificates, which the answer to it is unfortunately not, since if we want to get if and only if, so guarantees on these certificates, since we have this NP hardness problem, the best we can do the best we can do is the one the slide I showed before. And however, one thing we can do is modify this sort of allowed answer. So is the classifier F around the sample X adversarial free, right? That was the question. And again, if the algorithm returns yes, there are no adversarial examples within this radius, and then right now we want to allow the algorithm to return potentially not, which will mean that there are some adversarial examples, or it might be still adversarial free. And this is a more careful answer, since well, in case the algorithm says yes, we can be sure of its prediction, but in the other cases, we'll sort of decide on our own and not really rely on the model. Okay, moving on to one type of these certificates, robustness certificates. We have convex relaxation, where we sort of relax this classification margin that we introduced before. So before we had this optimization problem, right? And so in convex relaxation, we try to solve a relaxed optimization problem. So in this case, we would get an answer that is sort of worse, but still it will be perform faster, because the problem that we got was from ReLU, right? And then so moving on to this slide, we can see that ReLU does not have a convex output set, for inputs between this lower bound and upper bound that we had. And what this convex relaxation offers is that we change the output into this triangle and not the lines. So we should note that the output of the Rayleigh activation function is no longer deterministic. So we have x, and in this case, we won't really be sure where the x is and where the y is. So that would be another variable that we will need to optimize over, just similar to the input. Since now all of the constraints are linear and there's not even the binary variable that we had before, the a variable, we can solve this problem using a linear program and not a mixed integer linear program. Yeah, so the only difference here is that this part which sort of encodes the triangle. To give a more intuitive explanation to this convex relaxation, say we have this input x and we have this blue set of perturbations. And yeah, this does not necessarily have to be in a nice form. It can be, it can look like this. And yeah, we have this decision boundary here. We just created this this convex relaxation, this bigger set, bigger than the reachable perturbation set. And so when we had this zero perturbations, we get we get this classification here, and then for the worst possible classification margin, we got it as a lower bound to the no perturbation. And then here we can see that the green one, the one that we get from the convex relaxation problem, it is also a lower bound to this previous one. So obviously it's not as accurate as the one before, but the computation is much faster. So yeah, just forgetting the previous previous margin and focusing on this margin from the convex relaxation, if we get something like this, again, if this is positive, then we get a robustness certification. But in case our set is somewhere here and it's crossing the decision boundary, so for some example, for some perturbation, we have this this margin as a negative number, then we are not sure if it's adversarial free, since the correct set could be actually adversarial free, but this is a bigger set, so we can't be sure. Another thing I'll just really briefly go over is the robust training via duality. And just the general idea is that when we have this convex optimization problem, convex relaxation, we can reformulate the primal linear programming problem into a dual one, just as any linear programming problem. And even though this previous one that we got from the convex relaxation, it's tractable, it's still an optimization problem. And what this this duality gives us is that it gives another lower bound on it, on this previous margin that we got from the convex relaxation. And on the positive side, it does not have to be an optimization problem. It's just that any feasible point that we can put into this dual problem, G, it can be used as a lower bound to our original classification margin. And well, since G, the dual, is an analytic function, and then every feasible point will work, we can compute the gradients with respect to the neural network weights theta, and we can perform robust training with this. So just as a summary to convex relaxation, By relaxing this ReLU activation function, we turned our certification problem into a linear program, and that's easy and tractable to compute. And the only price that we paid is that there might be some instances for which we can't really decide if it's adversarial free around an epsilon ball. And so in the end, the result of the optimization problem will be an actual perturbed instance x tilde. And then we can also feed it into the original neural network and see if it's classified correctly or wrong. And again, so if it's not correctly classified, then it's an adversarial example. Then we also have this certification of no, it's not robust around this point x. And in contrast to exact certification, this lower and upper bounds on ReLU influence the quality of this relaxation, and so how tight this convex set will be, and how often sort of we will return maybe on the question. So as you can recall, in robust training, we wanted to optimize the robust loss with respect to the worst case perturbation. And so we solved this problem of supremum by replacing it with even larger value, which is tractable. But then the result obviously is not as accurate as it was before. And so in the slides before about duality, we instead of getting the bound using an optimization by solving an optimization problem, we use this concept of duality to find a lower bound that we got before. So just to mention the comparison to adversarial training is that the supremum was replaced by a surrogate right there, and then two points that are similar, that are the same in both cases, is that when we're computing the gradient of this bound or the surrogate problem relatively easy than in other cases I mentioned before. And again, we empirically get these machine learning models which are more robust. Okay, moving on to another idea is Lipschitz continuity. And roughly speaking, we want small changes in the input space to result in only a small change in the output space. And then adversarial examples actually lead to large changes in the output space. So this idea of robustness via Lipschitz continuity is to bound how much this output of the network can change for a given perturbation of this input x. And more formally, a function f is Lipschitz continuous if some distance metric on the outputs of two outputs of the neural networks of these two inputs x1 and x2, if it's bounded by a constant k times this distance metric in the input space between the inputs x1 and x2. And we refer to k as this Lipschitz constant and to f as being k Lipschitz. And yeah, these can be any metrics on this input and output space, such as LP norms. So the idea for this certification is to compute this Lipschitz constants for neural network F, and then well, how do we compute actually the Lipschitz constants? Is that when we're given a function, a composite function like this, the Lipschitz constant will be bounded from above by the Lipschitz constants, the multiplication of all of the Lipschitz constants of these individual smaller functions. So in case of a neural network with ReLU layers, or actually for now just any layer, we we will have here multiplication of the Lipschitz constants in every layer. Yeah, just as a result, we do get the this Lipschitz constant as the operator norm, where a W is the weight in this linear layer, and for p equal to 1, so for the L1 norm, we get it as the L1 norm of the columns of W, and then for p equal to infinity, we get the L1 norm of the rows of W, and for p equal to 2, we get the maximum singular value of the matrix of weights. And for convolutional weights, it's a bit trickier to compute, but can be approximated relatively efficiently. But we'll just focus on the Relu layers here. So yeah, for typical activation functions such as Relu, sigmoid, or tangent, hyperbolic, softmax, we have a Lipschitz constant of at most 1, and specifically for Relu, we have it exactly as 1. And for a neural network F with Relu activation functions, we again we can bound it with this formula, and this is also a sort of a regularization of the norm of the weight matrices. And so when we do this regularization on the weight matrices in our usual trainings, we can sort of we do sort of enforce this Lipschitz constant for the network. So suppose we have this this neural network F with the Lipschitz constant K. And so given an input sample X and this logits, so outputs before the softmax layer, we can compute the maximum norm epsilon of this perturbation, for which we can guarantee the robustness of the classifier. So firstly, we compute the minimum perturbation norm in the logit space that changes the classification. Then we compute the corresponding perturbation norm in input space based on this Lipschitz constant. And then after that, we can certify that for any perturbation in this perturbation set, which is described by this, the predicted class of any sample round X will not change. So it will be robust in this perturbation set. And if the Lipschitz constant K of this neural network is small, then we can expect to get more robustness certificates. So some practical considerations about this Lipschitz constant is that, from robustness point of view, we do want our classifiers to have small Lipschitz constant, but so for example, if we take the extreme that is 0 as the Lipschitz constant, it would mean that it will be impossible to change the prediction even though we have perturbations in the input space. But the bad part of this is that small Lipschitz constants usually limit the expressiveness of the function. And similar to any other type of method that I mentioned in this talk, we do have this sort of trade-off between expressiveness and robustness, or the performance or robustness. And also there are sort of theoretical limitations in using this only atomic Lipschitz constant to upper bound K. Okay. I don't think we have time for the final method that I wanted to mention, called randomized smoothing. So I'll just go to the overall summary of the talk. So the robustness, as we saw in this talk, the robustness of machine learning models is a crucial requirement in some real-world applications. And as we've seen, there are some multiple strategies for certifying the robustness of our models and for robust training. And these certifications that we covered were using these LP-bounded perturbations, even though there are some different types of other types of perturbations which do not change the semantic meaning of the inputs. But these are just the ones that are easier to work with. Yeah, so other relevant perturbations would be, for example, rotations or translations and illumination changes, which do give higher errors when we have these LP norms, but in reality, they would actually make up really meaningful perturbations. And while adversarial training is often easy to implement, even for these other perturbations, robustness certification is an active research field. Yeah, okay, so that was it. Thank you for your attention, and if there are any questions.
Thank you. We have time for questions. I have a question or a couple of questions. Generally, ensembling models is known to give robustness to the models, right? We have a couple of models. Does it also provide some sort of protection against adversarial attacks? I would presume so, right?
Well, the thing is that as I told in this talk, we sort of usually care for certificates, so for guarantees on robustness. And as far as I know, for these models, even though they're empirically robust, they do not have these sort of theoretical, robustness certificates.
But from practical point of view, I guess it's better.
Yeah, they're better. Just as regularization of weight matrices, it's also a sort of a solution to this robustness. But still, in these cases, we just have the empirical results.
One question regarding this. So we assume that the perturbation doesn't change the semantics, right?
Right.
And but is there a way like to compute? I guess it depends on the data set, right? How much epsilon you can have that doesn't change the semantics.
Yeah.
Is there a way like to compute some sort of like to give some upper bound or something?
Because so like the biggest
yeah, because I've seen that, for example, for MNIST data set, it's possible to actually construct some examples with very low epsilon, which actually changes the semantics, which can be problematic, right? Is there a way like, to give some upper bound on this?
Okay, so as you said, it depends very much on the data set, right? So because I don't know, MNIST is a black and white data set. It's a little bit different there, and there's small pictures, so I can't be sure in my answer, but I think that this is a rather subjective thing. So also for just for normal, like bigger images, bigger data sets, when you have some epsilon, then a bigger epsilon, I think that the point where it's already obvious, so it does change the semantic meanings, is sort of subjective, so it depends on who's judging that. But I'm not really sure, so that there might be some bounds on that. That's an interesting question.
Okay.